Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. When you cross that ill-defined line into the realm of big data, when your data no longer can reside on a single machine, you're forced to apply distributed computing. And while tools like MapReduce and Spark are certainly available and powerful for these situations, they don't give us an obvious out-of-box way of dealing with time series. Today on the show, I speak with Feng about the paper Distributed ARIMA Models for Ultra-Long Time Series.
My name is Feng and currently I work with Central University of Finance and Economics in Beijing, China. Yeah, I have background in statistical computing, and nowadays we focus on time series forecasting with large scale of data on distributed systems.
So I haven't yet had the chance to interview anyone specifically about distributed time series. It seems like that would be some extra challenges because, the data is sequential. What happened before relates to what happens next. How can you spread that across many machines?
A distributed time series is just a time series that is ultra long. It can be like billions of observations. Historically, we built up statistical models based on assumptions on stationarity and other assumptions, and those assumptions do not work on distributed system. And in industry, like Apache Spark, actually de facto standard for data processing. And in industry, people store a huge amount of data on distributed systems. So we have to make a model that really works on such distributed system, and we have to work on their language to make our forecasting more robust on this ultra-long series.
Yeah, Spark is naturally a good choice to use because it has such a good reputation and a lot of reasons to look at it for big data solutions. But it's not obvious to me that it's necessarily the right choice for time series because it's not really baked in, right? They've moved more and more towards like a SQL style and data sets. Are there any technical challenges to implementing time series via Spark?
Yeah, if you consider one single time series, that's fine. But if you think about what we are doing, we are streaming data. Data is like time series coming out, like water, like river coming out. Then you really need a non-stop system to processing the whole system data simultaneously without much delay. That is a demand for time series forecasting. And I have to claim that I think a lot of people agree with me. Nowadays, all data are in time series because when we collect data, we always have the timestamp. So that's we need time series for distributed systems. And it's a new challenge, I think, in many, many areas like atmosphere, electricity, energy, and other domains.
Good examples. The paper largely focuses on what you call ultra-long data sets. What is an ultra-long time series?
We made up this name, ultra-long time series. I think in time series, like 10 years, 20 years ago, people didn't call it ultra-long. People called it like high-frequency data, especially in financial domain. In financial domain, when you have stock market data, you observe like 5 seconds or 10 seconds. That is high frequency, so you accumulate a lot of data in a day. But at that moment, you only focus on next 5 seconds or next 10 seconds your option. Do you want to buy or do you want to sell? But now we have more and more data. In that fashion, you collect more high frequency, but you also need to predict in future, have much longer forecasting horizon, not only predict next 5 seconds, but you need to predict like next 24 hours or even next 4 months. That makes the time series like ultra long, not only in frequency, but ultra long in the forecasting domain.
Well, there are a lot of techniques I'm familiar with where you take advantage of distributed computing by sort of random sampling out of the data you have, distributing it out, and then averaging or aggregating back those independent models you've built. That's not really going to work great, or I assume it wouldn't work great for time series, because if you sample pieces, you're going to end up with holes in the time series. Do I do it that way, or do you break it into regions?
When you have independent data, it's okay, you random sample, you split them in subsets and aggregate them. But in time series, the data are sequentially connected. What can we do? We can do like blocks, like moving window, but make each window as a consecutive series and connecting all series together. But within each window, we can independently model those series. In the end, we can model the global activity between the windows. It's like you have very long time series, but you have some realistic assumption that at a certain level or inside a certain window, there is a possibility to fit traditional or conventional time series model. Then we have a technique to make all of those traditional models work like time varying fashion, so that essentially you gain this distributed systems advantage, but also what you do, you can maintain the time dependency over the long time interval.
That makes sense. Can you talk a little bit about how then you recombine those windows?
We developed a tool that is called least square approximation method. That tool essentially saying that if you build a time series model, let's say if we do a likelihood inference, then we can make this likelihood into small chunks of likelihoods. And for each likelihood, you can maximize that within that certain window. And in the end, you just do a least square method to find some optimal value. That optimal value parameter can work over all time domain and all time window so that you find some certain value theta both captures local feature. That is, like you have a feature works on local window, and that parameter also captures global time varying phenomenon.
I'm wondering if we could place this in the context of a fictitious example and talk through how the model would operate. I'm thinking of something like a website that is all about the Olympics. People care about the Olympics all the time, so it probably gets a good amount of daily visitors, but for sure there would be some sort of cyclic 4-year cycle where the interest would grow and then fall. So it seems ultra long because you have a lot of data points. Could even be like your hourly statistics if you want to stretch it out. And these events, this 4-year event that has this, very long lag, how would the system end up maybe figuring that out and taking advantage of that?
If we just consider that single time series and conventionally we do ARIMA model, from computational point of view, you could make ARIMA 1.1 or ARIMA 2.2 something, but you couldn't make ARIMA 365. That is very difficult and it's very computational demanding. What we do that for each small chunk of time, for example, could be within a few hours or within a few days, you can make a ARIMA model like ARIMA 315. Then in the end, you could have a lot of ARIMA 315, 342 or something. And in the end, for the long time span, you can put those small ARIMA models together. You will notice that for each ARIMA model, that model's local time or local seasonality effect within that certain level. And you also manage to combine so that last year's time effect will also be modeled because you combined, and that effect will come out in forecasting effects. So if you look at our application of our paper, you will notice that conventionally you just do a single ARIMA model, you will end up with a really stationary forecast. That is, according to theory, it is true. But with our distributed forecasting, we capture the very long but slowly changing time trend. That is the advantage, and that's how we do.
So if you want to benchmark your approach to, let's say, a monolith implementation where I get the biggest computer I have and I try and work on sort of traditional single thread approach to coming up with a forecasting model. Obviously, we can compare the two in both their runtime and their accuracy. Do you have any, high-level statistics on performance in this regard?
Yes. We had a test showing that. So when we have a relatively small chunk of time, there's no significant advantage by using distributed system. It's not that necessary. And when time series is really long, when you assume you have a supercomputer, large memory, and a single core, you will run, for example, 100 hours. That is typical true because when the length of data is accumulating, the computational time will be essentially exponential. You really spend a lot of time by reading and calculating all the likelihoods. But with our distributed system, we only need 2 or 3 nodes, and that work will be done within a few minutes. That means we essentially saved about 99% of computational power. That is very important in industry. If you use Amazon or Microsoft or other cloud computing, it's very expensive. Think about, you do a regular model, you run the model, that will cost like $100. Now use our distributed forecasting, only cost like $1. Which one do you choose? Obviously you choose ours. And in terms of accuracy, because our approach both captures local trend and global trend, we have better forecasting performance in the long run. That is an extra gain for doing with distributed system. In a lot of theoretical work, you will notice that people will only talk about, if you do distributed computing, you will gain some like consistent result compared to a global model. But with our result, we notice that we not only speed up computation, but also we improve the forecasting accuracy with a significant factor if you look at our application to electricity demand data.
Thanks to this week's sponsor, Quantum Metric. It's beach weather outside, especially here in Southern California, but for retailers, the holiday season has already begun. 2021 holiday e-commerce sales are expected to exceed 2020 benchmarks. Are you prepared to capture every customer opportunity? With Quantum Metric, you can be. Their unique approach to the digital customer experience helps today's top retailers and e-commerce brands quickly identify and prioritize the big and small revenue opportunities that keep customers engaged and coming back. They have the type of platform that any serious product owner in this space needs to take a good look at. Luckily, you can do that for free with their 12 Days of Insights offer. This sneak peek not only gives you access to their platform, but is coupled with a bespoke insights report that will help you identify where customers are struggling or engaging in your digital product. Some restrictions apply. Head over to quantummetric.com/podoffer and use code SKEPTIC. That's quantummetric.com/podoffer. Code SKEPTIC. Today, many small business owners are busier than ever. Time spent searching for and interviewing the wrong candidates for a job opening could be time better spent growing your business. That's why LinkedIn Jobs has made it easier to get to the candidates worth interviewing faster. And it's free. Create a free job post in minutes on LinkedIn Jobs to reach your network and beyond to the world's largest professional network of over 750 million people. Focus on candidates with the skills and experience you need. Use screening questions to get your role in front of only the most qualified people. Then, use the simple tools on LinkedIn Jobs to quickly filter and prioritize who you'd like to interview and hire. I have personally followed that simple advice and been very satisfied with the experience. Whenever I'm hiring, especially for an important role, LinkedIn Jobs is always one of the places I think to go to, top of list. Everyone's on LinkedIn, and I've always been satisfied with the quality and volume of candidates I get. LinkedIn Jobs helps you find the candidates worth interviewing faster. Did you know every week nearly 40 million job seekers visit LinkedIn? Post your job for free today at linkedin.com/dataskeptic. That's linkedin.com/dataskeptic, all caps, to post your job for free. Terms and conditions apply. Oh, that's very interesting. It almost seems counterintuitive. One would think that you would, as best, do equal to the non-distributed method. Do you have any insights into why it's actually an improvement?
The improvements basically come from 2 factors. One is that for an ultra-long time series, if you make that with one global model, conventional time series model usually have very strong assumption like stationary assumption. And those types of assumptions really do not work or do not compare with such long time series. So you actually made the wrong model, such long date. So you do ARIMA model for really long time series. That doesn't work. And second, because as I claim that, because we do distributed modeling, we managed to make each small chunk of the data modeled perfectly with a conventional time series model. And we also managed to connect those models over the long time horizon. That means we essentially make like non-parametric version of a combination over time, make the time series forecasting really time varying. That is advantage, and we overcome the conventional time series shortage, and we utilize distributed computing power.
I'm familiar, at least in like audio engineering, there's this concept of the Nyquist frequency, that if you whatever your sample rate is, it kind of gives you the minimum threshold of frequency you can measure. Do you have any equivalent in thinking about the windows? Is there some size limitations you have, and given, the effects you might discover?
In our experiment, we have some considerations. First one is that the window shouldn't be too short. The window should be like relatively long so that your conventional model works pretty well. You make sure that within each window you have enough observations to make a ARIMA model or other types of model works well, and the local features are captured, the first consideration. And the second, the local model doesn't have to be really long. If the local model is too long, that will make the local computation, like MapReduce task, the map part, really it will make the map part spend a lot of time to compute. That will reduce the overall computational efficiency. In our experiments, we noticed that if you make your local window like 10,000 or like 5,000, that should be sufficient.
Well, I'd love to dig deeper into the application to electricity data. We've talked a little bit already on the podcast about the importance of electric prediction just in having an efficient power grid and how critical and cost-effective good choices can be. Could you talk a little bit about the application of your techniques to that specific problem?
Now, we notice that in a lot of cities, households, they will be installed with a special metric to measure like every few minutes or every few seconds electricity usage. And electricity is a special types of resources, and you couldn't really store those power in a certain tank or something. So you have to plan that in advantage. And depending how do you produce electricity, if you use wind or if you use solar system, if you use coal and other systems, you really need to plan advantage. That could be like a month, or that could be like a quarter if we need to do a trading between, for example, China and Australia. You really need to make the decision half years ahead. That means you rely on very high frequency data, and you need to plan what will happen for next quarter. That will make time series long, and that actually require you to make a really long horizon forecast over the long time domain. Our distributed forecasting framework will make this high frequency captured carefully with local models, and we also make our distributed system to allow you to forecast like a quarter ahead, and that I think is very good in terms of this type of application.
Yeah, it seems like that's, if not state-of-the-art, close to it and worth considering for application, in an industrial setting. Do you know anything about next steps, or is there interest in people using this for real-world applications?
I have to admit that not so many forecasters are working on distributed systems, and I have observed in industry there is a lack of distributed forecasting tools. So we really need to make this gap between forecasting methodology and the distributed system. Our distributed models are some examples that make it possible to make solid forecasting theory works industry-level distributed systems. But this is not so easy because we need to learn distributed modeling and we need to learn distributed computing techniques. Luckily is that like Apache Spark, it has a very good Python interface. So if our forecasters have some knowledge on Python, and if they know a little bit about MapReduce, I think it is easy for them to make their own algorithm or own model make in terms of distributed computing, so they know how to split the model and how to make the divide and conquer approach. That is a fast and efficient way to do it.
In many distributed computing problems, you have to be very smart about how you partition your data. But I'm guessing we have an obvious partition key in the timestamp that you have for your time series. Is it as simple as that, or are there any words of wisdom you have for people embarking on solving an ultra-long time series forecasting problem?
A few factors we need to consider. First, that I have claimed that you have to make each chunk to be sufficient large enough to capture local feature. The second one, you need to think about distributed system. On distributed system, the data are partitioned into small blocks and stored on each distributed nodes. So you need to make sure that your chunk should be some size similar to the chunk size that is designed for distributed system. For example, if you work with HDFS, that is a Hadoop distributed file system, usually you have your chunk size that is 128 megabytes. So you could think about you want to make your time series that is for each small size that should be equivalent or should be a factor of this number, so that to make sure every window is inside a particular partitioned machine and the computation will not increase much communication. That will make your model computation really fast.
Good advice for sure. On each of these splits then, as you've been describing, you run an ARIMA model. And this is no surprise given how popular and powerful ARIMA is. But have you considered whether or not the technique would benefit from exploring other methodologies?
Yeah, we built up the foundation tool called DLLC, that is Distributed Least Square Approximation, that works with any objective function. And if you have a loss function that can be composed into small blocks, and if you want to estimate parameters with each loss function, in principle, our theoretical framework works well. And we have tested that with logistic types of model, all types of regression models, and the VAR model, and GACH models, and quantile regression models. So I think there is potential to extend to others, but we didn't have much time to validate, and maybe other researchers or practitioners may want to try with other models. There's a more particular requirement to work with our framework, yes.
You have a couple parameters in how the system works, like the number of sum series that you're going to analyze. And of course, we'd hope that small variations in parameters like that wouldn't affect the results too much. Could you talk a little bit about the sensitivity analysis?
When we do least square approximations, it's like a regression with least squares type of thing. You could consider the x is actually the observations you have obtained within each time window. For each time window, you have a lot of parameters, and x are just those parameters. And y, that is your best fit. You have your optimal theta. You want to find a certain x that this x is as close to all your other parameters, but make your overall loss as small as possible. So the fundamental work on this distributed least square approximation methods could guarantee really small error over that setting.
Where do you see this line of research going next? What are some of the fruitful lines of inquiry you think will improve upon the technique?
Yeah, a few aspects I could say. First, that we need to make more time series model that is applicable distributed system, or at least a large scale of time series data. Because when we notice that our time series model or our time series algorithm that works relatively short time series do not necessarily work with long time series. That is one challenge we need to do. The second one is that from computational perspective, we need to make user-friendly tools that the industry practitioners use that easily within distributed system. If we could make our framework like a standard module on Spark, that would be really useful for forecasters. And the third, we need to try other types of time series models, not like ARIMA types of models, but also think about the famous forecast tools in R can we conventionally easily transfer those type of models into distributed system, and that will take some time to validate, and I think there's potential.
Well, as people who read the paper will discover, you guys are releasing some source code for that Spark platform to go along with the research, so people comfortable in Python or R can both test it out. We'll have a link to the repository in the show notes. Would you talk a little bit about what people will find there and how they can get up and running?
We try our best to make it like a standalone Python package and to work with PySpark. So if you want to use that, you go to our Git repository and download it, and there is a run script. So if you open the run script, you will notice that if you can just package that whole repository and connect it with the Spark and link to the Spark system, that will be really, really easy to do it if you know how to upload data to Spark. And if you want to modify that piece of code, you could look into this algorithm section. You could change the least square approximation to other types of approximations, and you could also change the ARIMA model into other types of models, so that it will give you some extension to do it. You only need to know a little bit about Spark and a little bit about Python.
But that's a low bar. I think many people who don't have those skills can easily get them and then start experimenting with it. So very cool that this makes it accessible. Well, Feng, what's next for you? Are you going deeper into this line of work, or is this just one part of your overall spectrum of interest?
Yeah, it's just one part of my interest. I worked with time series forecasting, and we work with large-scale time series forecasting, and this is one part of our project called forecasting highly scalable and distributed systems. And besides this, we also work with statistical computing and other types of models, and we work with financial data. And I also work with econometrics and Bayesian methods. So I have pretty broad interest in terms of statistical computing.
And where can people follow you online?
Yeah, they can follow me on Twitter if you search for F3NG Lee. So actually Feng Lee if you replace E with 3.
I'll have that in the show notes as well so people can find it there too. Thank you so much for taking the time to come on and share your work.
Thank you so much.
That concludes another installment of Data Skeptic Time Series. Thanks to our sponsors today, Quantum Metric and LinkedIn. Our guests today, Feng Li, myself, Claudia Armbruster as Associate Producer, Vanessa Bly, Guest Coordinator, and our host, Kyle Polich.